What is force? Simple question. You use force every day. You push doors. You lift things. You throw balls. Force is everywhere. So you must know what it is, right? Wrong. Force is one of the most misunderstood concepts in all of physics. And the reason it's misunderstood is because we use the word in everyday language to mean something completely different from what it means in physics. Let me show you what I mean. You say, I'm using a lot of force to push this heavy box. What do you mean by that? You mean you're exerting effort. You're straining. Your muscles are working hard. That's what force means to you. But that's not what force means in physics. Not even close. In physics, force is not effort. It's not strain. It's not how hard you're working. Force is something very specific. And once you understand what it actually is, everything else in physics starts to make sense. So let me tell you, what is force? Force is that which changes motion. That's it. That's the definition. If something's motion is changing, a force is acting on it. If no force is acting, motion doesn't change. But what does change motion mean? It doesn't just mean speeding up or slowing down. It means any change in velocity. And velocity is speed and direction combined. So if something speeds up, that's a change in motion. Force is acting. If something slows down, that's a change in motion. Force is acting. If something changes direction, that's a change in motion. Force is acting. And here's the key insight. If something is moving at constant speed in a straight line, no force is needed, none. The motion continues on its own. This is Newton's first law. An object in motion stays in motion unless a force acts on it. Now your intuition rebels against this, because when you push a box across the floor, you have to keep pushing. If you stop pushing, the box stops moving. So clearly you think force is needed to keep things moving. Wrong. The box stops because friction is acting on it. Friction is a force. It opposes motion. When you push the box, you're applying a force that exactly balances the friction force. The net force is zero, so the box moves at constant speed. When you stop pushing, friction is still there. Now there's a net force, the friction force. And that force changes the motion. It slows the box down until it stops. So you don't need force to keep something moving. You need force to overcome other forces that are trying to stop it. In space, there's no friction. If you push something in space, it keeps moving forever, at constant speed, in a straight line. No force needed. You pushed once, gave it some speed, and now it coasts forever. That's the natural state of motion, constant velocity. Force is only needed to change that motion. Now, let's be more precise. Force doesn't just change motion. It causes acceleration. And acceleration is the rate of change of velocity. Newton's second law says, force equals mass times acceleration. F equals ma. What does this tell us? It tells us that force and acceleration are connected. If there's a net force, there's acceleration. If there's no net force, there's no acceleration. And acceleration means velocity is changing. So force causes changes in velocity. That's what force does. Let me give you examples. You're standing still. Are any forces acting on you? Yes. Gravity is pulling you down. The floor is pushing you up. Two forces. They're equal and opposite. They cancel. Net force is zero. So you don't accelerate. You just stand there. Now you jump. What changes? You push down on the floor. Hard. The floor pushes up on you. Harder than gravity pulls down. Now there's a net force upward. That force accelerates you upward. You leave the ground. While you're in the air, what forces act on you? Just gravity, pulling you down. That's a net force downward. So you accelerate downward. Your upward velocity decreases. Eventually it becomes zero. Then you start moving downward, faster and faster, because gravity keeps accelerating you downward. Then you hit the ground. The ground pushes up on you, very hard, harder than gravity. Net force upward. You decelerate. Your downward motion stops. Every change in your motion, every acceleration, every deceleration was caused by a force. Now here's something subtle. You're sitting in a chair, not moving. No acceleration. So the net force on you is zero, right? Right. Gravity pulls down. The chair pushes up. They cancel. Net force is zero. But you feel the chair pushing on you. You feel pressure on your backside. Doesn't that feel like a force? It is a force, but it's balanced by gravity. The net force is zero, so you don't accelerate. This is important. You can feel forces acting on you even when the net force is zero. Your body senses individual forces, but physics cares about the net force, the sum of all forces. That's what causes acceleration. Here's another example. You're in a car. The car is accelerating forward. You feel pushed back into your seat. What's the force? Your intuition says the acceleration is pushing you backward. Wrong. There's no such thing as a force of acceleration. Acceleration is caused by force, not the other way around. What's actually happening? The car is accelerating forward. The seat is pushing you forward. That's the force. The seat is accelerating you forward to match the car's acceleration. You feel that push. It feels like you're being pushed backward because you're resisting the acceleration. But really, you're being pushed forward. This is why physics is counterintuitive. The sensation you feel and the force that's actually acting are not the same thing. Now let's talk about what force is not. Force is not energy. People confuse these all the time. They say things like, I'm running out of force, or I need more force. What they mean is energy. But force and energy are completely different. Energy is the ability to do work. Work is force times distance. If you push something and it moves, you've done work. You've transferred energy. But the force itself is just the push. It's not the energy. You can apply a force without doing any work. Push on a wall. The wall doesn't move. You're applying force. But no work is done. No energy is transferred. The wall doesn't care how hard you push. It's not moving. Force is also not power. Power is the rate of doing work. It's energy per unit time. Again, completely different from force. You can apply a small force and generate a lot of power if you do it quickly. You can apply a large force and generate little power if you do it slowly. Force, energy, and power are three different things. Here's another confusion. People think force is a property of an object. They say this box has a lot of force, or this person is very forceful. Wrong. Force is not a property. Force is an interaction. It's something one object does to another object. The box doesn't have force. You apply force to the box. The box applies force back to you. That's Newton's third law. For every action, there's an equal and opposite reaction. Force always involves two objects. One pushes, the other pushes back. You can't have a force with just one object. It doesn't make sense. Now let's talk about types of forces, because there aren't as many as you think. In everyday life, you experience lots of different forces: pushing, pulling, friction, tension, air resistance, buoyancy, so on. These all seem like different kinds of forces, but they're not. They're all the same force. They're all electromagnetic force. All of them. When you push on something, what's really happening? The electrons in your hand are repelling the electrons in the object. That repulsion is electromagnetic force. When you feel friction, that's electromagnetic forces between atoms. When you feel tension in a rope, that's electromagnetic forces holding the rope's atoms together and resisting being pulled apart. Every contact force, every force you can feel, is electromagnetic. So how many fundamental forces are there? 4, just 4. Electromagnetic force, that's the one you experience most directly. It's what holds atoms together. It's what makes chemistry work. It's what you feel as pushes and pulls. Gravitational force, that's what pulls you toward the Earth, what keeps planets in orbit. It's much weaker than electromagnetic force, but it acts over long distances and it's always attractive. So for large objects like planets and stars, gravity dominates. Strong nuclear force, that's what holds the nucleus of an atom together. Protons and neutrons are held together by the strong force. It's the strongest force, but it only acts over incredibly short distances. Inside the nucleus, and that's it. Weak nuclear force. That's responsible for certain kinds of radioactive decay. It's weak. It acts over short distances, and you never directly experience it in everyday life. 4 forces, that's it. Everything in the universe, every interaction, every push, every pull, is one of those 4 forces. Every force you've ever felt is electromagnetic. Gravity keeps you on the ground and keeps the Earth orbiting the sun. The strong force holds atomic nuclei together. The weak force makes certain atoms decay. 4 forces explain everything. Now here's something that bothers me, and it should bother you too. I've told you what force does. It causes acceleration. It changes motion. But I haven't told you what force is, and here's the truth. I can't. Nobody can. We don't know what force is at a deep level. We know how it behaves. We know how to calculate it. We know how to calculate it. We know its effects, but we don't know what it fundamentally is. Is force a field? Is it an exchange of particles? Is it a curvature of space-time? Different theories give different answers. In quantum mechanics, forces are caused by exchanging particles. Electromagnetic force is mediated by photons. Strong force by gluons. Weak force by gluons, by W and Z bosons. Particles are constantly being exchanged, and that exchange is what we experience as force. In general relativity, gravity isn't a force at all. It's a curvature of space-time. Massive objects bend space and time around them. Other objects follow the curves. They're not being pulled. They're following the straightest possible path through curved space-time. It just looks like a force. So even physicists don't agree on what force fundamentally is. We have different models, different frameworks. They all make predictions. The predictions work, but they give different pictures of what's happening underneath. And that's okay. That's how science works. We have models. The models are useful. They let us calculate things, predict things, build things. But the models aren't the reality. They're descriptions, approximations. Force is a useful concept. It helps us understand motion. But at the deepest level, we don't really know what it is. We just know how it works. And here's the thing. You don't need to know what force fundamentally is to use it. Engineers use force every day to design bridges and buildings and cars. They don't worry about whether force is a field or a particle exchange. They just calculate the forces, apply Newton's laws, and build things that work. Physics is like that. You can use concepts without fully understanding them at the deepest level. You can make accurate predictions without knowing the ultimate nature of reality. Does that bother you? It bothers some people. They want physics to give ultimate answers, to tell them what things really are. But physics doesn't do that. Physics tells you how things behave, how they interact, how to predict what will happen. It gives you models, equations, frameworks. Those are incredibly powerful. But they're not final truths. So what is force? Force is that which causes changes in motion. Force is measured in newtons. Force follows Newton's laws. Force can be calculated, predicted, used. But what it fundamentally is, I don't know. Nobody does. And maybe we never will. And that's beautiful, because it means there's still mystery, still things to figure out, still deeper levels to explore. Physics isn't about having all the answers. It's about asking better questions, building better models, understanding more deeply, always pushing forward, always wondering. Force is one of the most basic concepts in physics, and we still don't fully understand it. That should tell you something about how deep the rabbit hole goes. But here's what we do know. We know how force works. We know how to use it. We know how to calculate it. And that knowledge lets us build rockets, design bridges, land rovers on Mars, predict planetary orbits, understand the structure of atoms. We don't need to know what force ultimately is to use it effectively. And that's one of the great triumphs of physics. We can make accurate predictions and build working technology even when we don't fully understand the fundamental nature of things. So, what is force? Force is a concept. a powerful, useful concept that lets us understand and predict motion. It's the thing that changes velocity, the thing that causes acceleration, the interaction between objects. And if you want to know what it really is, at the deepest level, join the club. Physicists have been asking that question for centuries, and we're still working on it. That's not a failure. That's the beauty of science. There's always more to learn, always deeper to go, always new questions to ask. Force is fundamental to physics, and we still don't fully understand it. And that's exactly as it should be.